The remaining examples we'll look at now involve the kinematics formulas that we looked at in chapter 1 and work. So cars accelerating at 1.8 meters per second squared from 7 meters per second to 12 meters per second. How much work is done if the acceleration force is 1850 newtons? So the first part here, we know that work is force times distance. So start with what you know. Start with this formula and see what you can put in. That'll give you a hint on where you need to go next. So if we put in our 1850 newtons, what we realize is that we don't know our distance. So we need to look back at our given information. And when we look at our given information, we have the acceleration, v1, v2, and need to find distance. So here you're going to have to look back to your kinematics formulas, and remember there is a copy posted to the course website. And when we look back, you should find you need a formula that involves distance and the other three values. So here, fill in your acceleration, your v2, your v1. Let's solve for d. And again, I'll go a little faster through this because this was already covered in Unit 1. If you have problems with it, please let me know. This side should work out to 95. You have 3.6d. Solve for d. So you divide by 3.6. And you have a distance of 26.4 meters. So we come back to here. Put in your 26.4. And the answer should work out to 49,000 joules. If you want to write in scientific notation, 4.9 times 10 to the 4 joules. Okay, in the next example here, we have a 20 Newton right force that's applied to a hockey puck as it slides along a frictionless surface from rest to 10 meters per second. And it does this in 0.2 seconds. So here's our hockey puck. Force is applied to the right. It's 20 newtons. We know the mass of the puck. And we know the beginning velocity, 0. We know the ending velocity is 10 meters per second. And that's after 0.2 seconds. Oops. Okay, so let's say you solve that now on your own. You start where work is force times distance. And you know that force applied was 20 newtons. And it's in direction of motion, so we don't need to worry about cosine theta. And you get stuck here. What's the distance? Well, let's look back to what we know. We have v1, v2 time, and we have to find distance. So if you look back to your kinematics formulas, this is the formula that applies. A half times v1 plus v2 multiplied by time. So v1 plus v2 divided by 2. Dividing by 2 is the same as multiplying by a half. So take your two velocities, add them together, multiply them by a half, or divide by 2. That's the same. And then multiply by your time. You come back with 1 meter. So here put your 1 meter back in. And you have 20 joules, or 2.0 times 10 to the 1 joules. Alright, in this example, calculate work done on a cyclist if a braking force of 40 newtons backward slows the cyclist from 20 meters per second to 15 meters per second in 2 seconds. So the braking force is going to be acting against the direction of motion and slowing the cyclist. So we start with work. It's force times distance. And we're going to need to use cosine theta here, because since the braking force is opposite the direction of motion, the motion in this case is going forward. Braking force is going opposite to that. So theta will end up being 180. So you know that at this point. And you have the force, which is 40 newtons. And you need to find the distance traveled. So if you look at the information you're given, you have V1, V2, you have time, and you need to find distance. So V1, V2, time, and distance. You pick your formula from here. I'll give you a moment so you can find the right formula. And the correct formula is the same one that we had used last time. Here. Alright, now we work our formula out. Take a formula, applying the numbers that we know our velocities, and you should work out to a distance of 35 meters. So you come back, put in your 35 meters, you know your force. Cosine is going to be 180, because again it's opposite the motion. And you would work out to negative 1400 joules.